Alright, welcome back. This is going to be the last video for Unit 2 before you complete your Unit 2 progress checks and take your Unit 2 test. And in the last video, we introduced when one point is really a problem in terms of linear regression, whether it's an outlier and it doesn't fit the trend of the rest of the points, whether it's a high leverage point that's really far away in the x direction from the rest, or whether it's an influential point, which would influence something about the association, whether it's the slope or intercept of the line, or whether it's inflating the r-squared value, or whatever. And those are issues that you need to know how to take care of. If that point is a mistake, take it out, run the regression again. If it's a valid data point, you gotta keep it in there. Well, what if you've got a data set that's just not linear in any way? It's not even close. Like, you look at the scatter plot and you're like, not a line. What can we do? Do we just give up? No, there's still some tricks we have up our sleeve. So let's say, first of all, let's say we've got a data set and we know, either by looking at the scatter plot and seeing the trend, or maybe we have some information about these variables, we know the relationship is quadratic. We know that y is proportional to ax squared. So if you plot x versus y, you get a parabola, or at least part of it, right? You get this curve. But we want to do the linear regression with a straight line, but it doesn't make sense to fit a straight line to this. Okay, we can do it. Nothing's stopping us. We can put this data into our calculator, look at the scatter plot, it looks like this, and then do linreg, and it would fit a straight line to this curve. But that would be awful. Mostly because what you would see on the residual plot would be something like this. And that's not what you want to see on the residual plot. You want to see random scatter. And this is going to make it even more obvious that by fitting a straight line to this curve, it would look something like probably this. Those are the residuals. Clearly a pattern there. Linear regression is not appropriate. So, if x versus y gives us a curve that's quadratic in nature, how can we take this x squared and make that just x? So that it would be y is proportional to x, which would be linear. How do we get rid of something squared? We take the square root, right? So we just need to take the square root of x here. So, in a sense, we'd be doing y is proportional to a square root of x squared. Right? And this is just x. And this is a linear relationship. So what we're saying is, if instead of x versus y, you plot the square root of x versus y, you're going to see still a positive relationship. As x increases, y increases. But by taking the square root, by transforming this variable, that relationship is now linear. And now it makes sense to do linreg on this. We could get a regression line, and we can do all the things we talked about with linear regression once we've done this transformation. Pretty cool, huh? We can take a curve and make it a straight line if we know something about the relationship. What some of you might be thinking is, how can you just do that? Like, if you've got these x values in the original data and you take the square root, these are now different values. if you do a linear regression based on the square root of x here, those are different numbers, right? You've changed the data. How is that appropriate? Well, see, the thing is, later in this video, we're going to find you can do a linear regression on this transformed variable, and you can still interpret the results based on the original units, as long as you do the right inverse operation, right? We took the square root of x to get this. In order to interpret the results of this, we're going to have to take something and square it to get it back to the original units. But that is totally acceptable. We are allowed to do that. Okay, I don't want you to think we're doing some kind of voodoo here that makes this data different. It's still the same data. We're just making it into a straight line so we can do linear regression. That's totally okay. All right, hopefully I've assuaged your fears there. Okay, but not all relationships are quadratic. What if you know, based on looking at the scatter plot or the nature of the data set, whatever, that you have a relationship that is a power relationship. There is an exponent here, but you don't know what it is. So here we knew that exponent was 2 because it was quadratic. What if we know the relationship looks like this, but we don't know the value of the exponent? Well, there is a transformation that we can do still. And similar to what we did here, we want to get rid of this square. We want to do the inverse operation of something squared, so we took the square root. What is the inverse operation of an exponent that's unknown? How can we get this exponent out of the exponent? Algebra 2, we take the log. We're going to take the log of both sides. So we've got log of y, whoops, and the log of ax to the p power. Okay, so we took the log of both sides. So this is really the log of that quantity, the log of ax to the pth power, and this is multiplication. So if we've got the log of a product, then on this side, we can take log of a plus the log of x to the p power. You don't have to remember all these properties, but we're showing you if you've got a power relationship between x and y, we're trying to get at how we can transform the x to make it linear. Okay. And one more power of logs. The whole point is that we want this p out of the exponent. If this is a log, then that p can go out front. So we get this, p log x. Now notice, this is a linear relationship. Okay? This is just a constant, so it doesn't really matter. Right? So the log of y is proportional to p log x. Since we're just talking proportion here, the p doesn't matter either. So log of y is proportional to the log of x. So if you've got a power relationship, but you don't know what the exponent is, you want to transform both variables, log of x here, log of y as well. And that will turn your curve, again, into a straight line. Okay? So sometimes we only transform the predictor variable, the explanatory variable. Other times, we transform both. It also turns out, if you've got a nonlinear relationship of any kind, and you can't quite put your finger on what it is, this transformation where you take the log of both x and y is what some people call the Goldilocks model. It's the model that tends to do a good job in a wide variety of situations. So if you're trying to do linear regression on a data set that is bivariate and it's not linear and you need to transform it somehow and you're not sure how, this should be your first stop. try taking the log of x and y. And that's really easy to do on your calculator. If you ever need to do it for yourself, put your x in L1, put your y in L2. In L3, just type in L3 equals log of L1. L4 would be the log of L2. Simple enough. It doesn't really matter. When we say log here, going back to your prior math courses, we're assuming that this is log base 10. Right? If we don't write the base there, it's assumed to be 10. This is the same thing as the natural log, which has base e. These are interchangeable. Okay? Neither one is better than either. Like, they're both about the same. Okay? All you're doing is changing the base. It's going to make the same kind of transformation here. So if you prefer log base 10, use that. If you prefer log base e, use that. Okay. There is one other type of relationship that is fairly common when you're looking at scatter plots that are nonlinear. You can have a quadratic, in which case you take the square root of the x variable. If you have a power relationship, do what's called the log-log transformation. Take the log of x and y. And the other one is if you've got a relationship like that. Do you remember what kind of relationship this is? If the variable is in the exponent, that's exponential, right? So if you've got an exponential relationship, again, we have to draw on our algebra skills to get that x to be not an exponent, so that it's a linear relationship. If we need to get something out of an exponent, we're going to do the same trick we did here. Take the log of both sides. Oops, proportional. I don't want to call that an equation. Okay. So again, this is a product. The log of a product is the same as the sum of the logs. So this is log A plus the log of b to the x power. Then we can bring that exponent down. And we've got this. I'm going to rewrite this slightly. Okay. Log of b, assuming that a and b are just constants, right? This is just a number. So I'm putting it in front of x because it's kind of like 5x. You know, log of b is just a number. Okay. So if log of y is proportional to this, we don't really need that. And this is really not doing anything either. So we've got log of y is proportional to x. So this is if your original relationship is exponential in shape. You can tell that from a scatter plot as well. It turns out you only have to transform the y variable and take the log of it. Okay. This is if you have, if there is a power relationship, unknown power, let's say. And so if you've got a quadratic relationship, take the square root of x. If you've got an unknown power relationship, take the log of both x and y. And if you've got an exponential relationship, just take the log of the y variable. Those are the three most common transformations that will turn curved scatter plots into straight ones that you can then use linreg with and do all the fancy things that we've talked about in the last few videos. What if you're not sure, right? Maybe you run all three of these models because you don't know the difference between quadratic or power or exponential. You don't know. So you run all three. Well, if you run each of these 3 linear regressions, you're going to get a residual plot for each one. It is absolutely paramount that that residual plot looks like random scatter. If any of these models give you a residual plot that still has some kind of pattern involved, whether it's curved, still a linear pattern is still not what we want to see, or increasing variance, that fan shape, those models are not appropriate. Your model needs to have random scatter in the residual plot. Okay, that is absolutely number one. A good or a proper transformation will result in a residual plot with random scatter. Okay. Any kind of pattern, any kind of fan shape of increasing variability, that's a no-go. And it's possible you could run all of these transformations and still not get this. In which case, you still can't use any of these models. You'll have to find something else, or maybe just nothing will work. It's possible for no transformations to really work that well. But you need that. Let's say you run these 3 models for a data set, and more than one of them give you this. How do you choose between them? Well, a tiebreaker. Whichever model gives you the highest value of r squared, the coefficient of determination. Okay? That'll be your tiebreaker. Whichever model gives you that is the winner. And I have fond memories of my time at the Census Bureau. This is all I did for weeks at a time to determine which transformed model had the best fit for our data set. I worked with seasonal adjustment. So like in November and December, stores like Walmart, Dick's, any kind of retail really, sees a spike in their sales because of the holiday season. And so every fourth quarter, retail would be like, oh man, retail had a great quarter. But they always have great fourth quarters, right? It's the holiday season every year. So the concept of seasonal adjustment is saying, well, yes, the numbers went up, but were they up higher or lower than what we would have expected normally? And so I ran these kinds of models to determine whether it was higher or lower than expected. And what I did was I looked at these things. I wasn't necessarily running linear regression. I was doing a different type of thing entirely. But this concept of using the highest R squared model, that was super important for me. So I have real life experience using this tiebreaker because I was running a dozen models, not just 3. Okay, and that's what we use too. So this isn't just some like really dumbed down thing. Like this is real. We do that to use which model is best. So we talked a long time ago. I talked a lot about how this is not fake. How when we do these transformations, we can still get valid results, but we have to turn the units back into their original units, right? If we take the square root or the log of something, we have to undo that if we're going to interpret the results. So let's take a look at what that looks like. Here's an example I stole from a different textbook. How is the braking distance for a car related to the amount of tread left on the tires? So we all know, well, maybe we do, that it's really bad when all the tread is gone from your tires because then, like, it's not really stopping correctly. So there's like an optimal tread that's supposed to be on your tires. And this is what they're looking at. So they collected data on the braking distance measured in car lengths for a car making a panic stop in standing water along with the tread depth of the tires in 1/32 of an inch. So they did a linear regression for 3 different models, kind of like what we just showed up there. And they are giving us the residual plot for each model. So model 1 is based on the original data, so x versus y. Models 2 and 3 involved some transformations. So here is the output for the first model. This is just x versus y. And you can see the residual plot here. Okay. Model 2, they took the natural log of both x and y, braking distance and tread depth. And we get a residual plot that looks like this. Third model, they took just the natural log of braking distance. So this was the natural log of just the y variable, which is the last model that we talked about as well. And they get a residual plot that looks like this. So what they want to know first, which model does the best job of summarizing the relationship between the 2 variables? Explain your reasoning. You can pause the video and think about it, but if you already know, I'm about to say it, spoilers, it's model 2, right? It's the only residual plot you see that doesn't have a clear curved pattern in it. Okay? If I were running this model, I would still be concerned about different, like, it's like a fan shape in reverse. It starts out really wide and then narrows. Can you see? Yeah, kind of, right? It's really wide here and then it narrows here. But there are so few points in this data set, it's really hard to get random scatter. Like, there are only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 points here. It is very difficult to get random scatter from a data set of 11 points. We'll just settle here. Of these 3, it's the only one that doesn't have a clear pattern, so it wins. I wouldn't say it's perfect, but it's definitely the best of the 3 because the residuals don't have a clear pattern. And then for part B, it wants us to use the model that we chose in part A, which is going to be this one, to calculate and interpret the residual for the trial when the tread depth was 3/32 of an inch and the stopping distance was 13.6 car lengths. So, if you know what you need to do to answer this question, pause the video, go for it. Do it. We'll go through the answer in just a sec. But we're going to be using the output here. You're going to need to be able to construct the model based on this information. And it's a little more complicated than when we did it the first time because, notice, we've taken the natural log of x and y. So it's not y hat equals a plus bx. It's going to be the natural log of y hat equals a plus b times the natural log of x. Let me show you what I mean. Okay, let's write the model that they're doing in this case when they've done the transformation. So this is the basic linear regression model that we've talked about in the past. Okay? So the first step to getting to this one is let's plug in the variables for the explanatory and response variables. The variable we are predicting is whatever was on the y-axis of the original scatter plot. Given this output, it's easier to determine which variable is the x variable because it's the one that's here. It will always be here. Okay, so since we're talking about the natural log of tread depth in the model, that's going to be x. So I know that's tread depth, and that makes y the stopping distance, or braking distance. And also, you see here in the title, right here, in this computer output, if it looks this way, the first variable listed is going to be y, and the second will be x. So you also could have used the title here to show that braking distance is y and tread depth is x. But we said we're taking the natural log of both of these variables, right? So it's actually the natural log of braking distance equals A plus B times, A plus B times. That's an L, not like a capital I or anything. Some students get confused. Plus B times the natural log of tread depth. Okay. We haven't used really the numbers in this table yet, but we're going to write the model this way because we've done the natural log transformation. So the only thing left to do is to plug in the intercept and slope from this table. So we've got the natural log of braking distance equals the intercept, the y-intercept of this model, is where it says constant here, and it's the coefficient of the constant because there's no variable in this term, and that is 2.9034. Plus b is the slope. That's going to be the coefficient in front of tread depth, or the natural log of tread depth in this case, which is going to be that negative 0.269. So this is actually minus. Okay, so that's the model we're working with. And they wanted to know something. Hold, please. What did they want to know? I don't remember. Okay, so the residual for the trial when the tread depth was 3/32 of an inch and the stopping distance was 13.6 car lengths. Cool. Okay, so the tread depth is 3/32 of an inch, but it said originally in the problem this was measured in 1/32 of an inch. So we're going to be plugging in 3 here. I'll give you a chance to plug in 3 there. Oh, actually, let's just do it together. It's fine. So we're going to take the natural log of 3 here. I'm going to grab my calculator. I definitely need that. I usually have it out. What's my problem today? Axio calculator. Okay. So I'm taking 2.9034 minus 0.269 times the natural log, which is, sorry, I don't have my virtual calculator today. Focus. Nope. This is the natural log key. On this calculator, it's right next to the 4. So if I do that, it does ln, and I'm putting in 3. So I've got this. I know that's blurry. That's my bad. I didn't get my virtual calculator out today. Okay, and that gives me 2.608. So I get the natural log of my predicted braking distance is 2.608. So in the past, when we plugged values in for our explanatory variable, when we got this value, we were done because this was just y hat. But this is the natural log of the value we're interested in. So what do we need to do to this number to get it to be just estimated braking distance here? You do actually need to know this for problems you may need to do. The inverse operation of a natural log is taking e to the power of this number. So we're taking e to the power of both sides. These operations cancel out. So you get estimated braking distance equals e to the 2.608 power. To get this on your calculator, the ln button, if you do second ln, it does e to the power of. And then you just do your 2.608, And you get 13.57, and it's measured in car lengths. Okay. So, for a tread depth of 3/32 of an inch, it's predicted that it would take 13.57 car lengths to stop the car. Is that what the question asked? I don't remember. It's on the screen, but it's really small. Use the model chosen to calculate and interpret the residual. The residual! This is not the residual. This is what we predict for the car. This is what the line says the value should be. But the actual value was 13.6. So the residual, remember that's y minus y hat. That's the true value minus the predicted value. The true value, it said, was 13.6 car lengths. But we predicted 13.57. So that's going to be 0.03 car lengths. Hey! 0.03 car lengths. Yay. Okay. So the only real difference that you saw in this problem that we haven't done in the past is that once you got to this point, you have to do that inverse operation of the transformation you made. If you took the natural log, you have to take e to that power. If this were a log log, you would have to take 10 to the power of this number, because that's the inverse operation of a log base 10. If you did the square root of something, that would usually be the square root of x. You would just plug in whatever the value of x was there and take the square root as part of this, and it would work just fine. It's really only when you're messing with the y variable, the response variable, that you have to worry about taking the inverse operation. Okay, so that's usually either going to be the natural log, which e to that power, or if it's log base 10, take 10 to that power. Okay, there is, if you want more practice, because that took a while and this video is much longer than I wanted it to be. If you want more practice on Canvas, you can see I have this worksheet for you. If you want more practice doing problems like this, where you're taking values of the explanatory variable and predicting the response variable with transformations, you can look at this. And if you open that, you will not see it on the screen. You will see this. Okay, there are 6 problems here where they give you the regression equation. Each of them have been transformed somehow. So this one, they took the square root of y, and they want you to predict the cost given a value for the explanatory variable, and you would do that. Okay, this one, they took the log of y. This one, they took the cube root of y. This one is log on x and y. This is the log of y. This is square root of y. Okay, and in addition to that, I have also given you the key. So you can see the key as well, and that gives you the answers, obviously, so you can see if you've done them right. If you have any questions over those problems, reach out to me, email, whatever, Zoom, and we can talk through them. I will do them with you, if that's what you would like, because this is a common type of question on the free response of the AP exam. I wouldn't even be surprised with a relatively benign transformation like square root or something. It could be on a multiple choice question. So, yeah, and it could be on your test as well. Who knows? So, that's the end of Unit 2. That's everything you need. We zipped through these 2 chapters, 8 and 9 in the textbook, pretty quickly, and that's because usually transformations aren't emphasized really heavily on the AP test, and really you get more into this in future classes. This is just an intro stats class we're not going to get too far into this stuff. This is about as deep as we're going to go. But you've got progress checks that are due very soon. I think they're actually due the night that this video is assigned for, so make sure you do those. The live progress check review will be at 1 o'clock the next day. So if you want to talk about the progress check with me live, not in person, but on Zoom, you can do that as well. I would hope that the people that came to the one for Unit 1 think that it was a good use of their time and that they were more confident on some of the concepts of the exam than before they did it. And you will have your unit test also later this week. You will take that, and then we will get started on Unit 3. So there's a lot going on right now. At the end of a unit, that's really when you have all these things, and I apologize that it has to be that way. There's also homework for chapters 8 and 9 in the textbook, although those problems shouldn't take you all that long. So it is a lot, but you can do it. I believe in you. And it'll be a while before the end of the next unit, so you'll be able to breathe in between. I promise. So reach out to me if you have any questions about what you go through. And other than that, we'll see you in the next video.